We just saw a couple of videos illustrating the Doppler effect. One of those videos gave us a definition of the Doppler effect, and that definition was the apparent change in frequency, not the real change in frequency, but the apparent change in frequency. Once a wave has been made, the frequency never really changes. It's the apparent change in frequency of a wave due to the relative motion of the source and the observer. So you've got something that's moving relative to something else. One of the things is making a sound or making some kind of wave. The frequency will appear to change as a result of that motion. When a car is coming towards us and sounds its horn, it produces an actual frequency. It appears to us to be higher than it really is. And the reason that it appears to us to be higher than it really is because as that sound is coming towards us, the source is coming towards us, the waves kind of get scrunched together as it's coming towards us, makes it appear as if we're getting a higher frequency than we really are. But as it's going away from us, the waves get spread out. So it makes it appear as if the sound or whatever wave that we're dealing with has a lower frequency than it really does. The real frequency of the sound is somewhere in between. When you saw that video of the van driving by sounding its horn, or the fire truck driving by with the siren going, you never really even heard the real frequency. You heard what sounded like a higher frequency as it was coming towards us, and what sounded like a lower frequency as it was going away from us. The true, actual frequency fell somewhere in between. The last equation of the year. And it looks like kind of an ugly one. FD is equal to bracket VW over VW plus or minus, what? VS times FS. Let's identify what some of these variables mean. FD, that's going to be a frequency, right? We call that the Doppler frequency, or the apparent frequency, the frequency that we think we hear. Not the real frequency, but the apparent frequency. Remember in the video, Sheldon said that the Doppler effect is the apparent change in frequency. This is the apparent frequency, the frequency that we hear versus the frequency that's actually produced. And the units for that are going to be hertz, of course. Fs, on the other hand, is the frequency of the source, which is the actual frequency, the real frequency, the frequency that we don't actually hear when it's coming towards us or when it's going away from us. We hear a Doppler frequency that's higher than the real frequency, than the frequency of the source when it's coming towards us. We hear a Doppler frequency that's lower than the source frequency when it's going away from us. The source frequency is somewhere in the middle. What do you think V stands for in this equation? VW or VS? V is speed, right? But speed of what? You got to be careful out here. VW is the speed of the wave. That's usually sound. Okay, that's usually the speed of sound, but not always. It could be some other wave as well. You ever hear of red shifting or blue shifting in the context of astronomy? Okay? When something that's generating light is moving towards us or away from us, the light appears to change frequency. If it's going towards us, the frequency would be higher than it really is, and it would blue shift. Okay, if it's going away from us, the frequency would appear to be lower than it really is, and it would red shift. So what happens with light and other waves as well, but the way that we usually experience it, us, okay, everyday people usually experience it, is with sound. So we'll call it the speed of the wave, but it usually ends up being sound that we're dealing with. The reason they call it VW is because it is, in general, a wave. But a lot of people will get it confused with VS. People will look at VS and say, oh, that's the speed of sound. No, 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 no. This equation is a general equation, not unique to sound. It's valid for any wave. It just usually is applied to sound. We don't have a sound subscript in this equation because it's not just for sound. Vs, on the other hand, stands for the speed of the source. So it would be the van that was coming towards us in the first video that we showed you, or it would be the fire truck that was coming towards us in the second video that we showed you. The speed of the wave, Vw, and the speed of the source, Vs. And of course, the one on the top, Vw, is also the speed of the wave. Now, what's the deal with this? What's the deal with a plus or minus? Yeah? No, that's a good guess, but there's not two answers, actually. No, there's not two answers. Yeah? No, not the direction either. Another good guess there. JC?
Would it work both ways?
No. No, it doesn't work both ways. We're going to have to pick, go ahead.
Does it have to do if the thing is moving toward you or away?
Yes. We have to pick one or the other, plus or minus, depending upon whether it's coming towards us or away from us. Now, if you're like me, you're not very good at remembering things like this, right? Is it plus or is it minus? Remember we talked about diffraction, and I said, I'm not very good at remembering how the frequency affects diffraction, right? I know now that the lower the frequency, the more diffraction we get, but I know that only because I have a way of remembering that, right? Remember my apartment at the bottom of the hill was able to hear AM radio waves, low frequency, so that meant that AM or low frequency diffracted more than FM or high frequency. That's the only way I remember that. I'd never remember that if I didn't have a way of remembering it. I wouldn't remember this either if I didn't have a way of remembering it. Here's how I figure this one out, whether I use a plus or a minus when it's coming towards me or away from me. If it's coming towards me, you know from the videos that you saw, you know from experience in life, that the frequency appears to be what? Lower or higher? Higher. So if it's coming towards me, the frequency must be higher. If this frequency, this Doppler frequency is higher, then this number on the bottom must be smaller. To get a big number here, you get a small number here. How do you get a small number here? By adding or subtracting? By subtracting, right. So we're going to make this a minus or negative if the source is coming towards the observer. And we're going to make it positive if it's moving away from the observer. Right, if I make that a negative number, then the number on the bottom, the denominator, becomes a small number, and FD becomes big. If I make it positive, then that's going to become a big number on the bottom. That's going to make FD smaller, and it's going away. Now, some of you are going to be just better at remembering that than me. I'm not good at remembering that. If you were to ask me 15 minutes ago whether it's a plus or a minus on the bottom there, coming towards or going away, and you didn't give me 5 seconds to think about it, I would have had a 50-50 chance at getting that right. I would have guessed plus or minus. Okay? I don't remember it. I figure it out each time. Okay? But the good news is, if you have some logic, like you can figure it out in 5 seconds or less, and you're always going to be right. You don't need to worry about getting the wrong plus or minus. It's always going to be right. Okay, let's take a look at an example, the last example, in fact, of the year. This train is traveling at a speed of 30 meters per second. Its whistle generates a sound wave with a frequency of 224 hertz. You're standing beside the tracks as the train passes you with its whistle blowing. What change in frequency do you detect for the pitch of the whistle as the train passes if the speed of sound is 330 meters per second? So this one's a little bit tricky, actually, because we're not looking for the Doppler frequency, the apparent frequency, as it's coming towards us or as it's going away from us. We're looking for the change in frequency. So we need to find the frequency as it's coming towards us. We need to find the Doppler frequency as it's going away from us, and then do what? If we're looking for the change, we've got to find the final, the initial, and then subtract them, right? All right, let's figure it out. We know that the speed is 30 meters per second. We're going to call that this Vs, the speed of the source, because the train that's making the sound is 30 meters per second. The speed of the wave isn't 30, but the speed of the source is. It generates a frequency of 224 hertz. Is that going to be FD or is that going to be FS? The apparent frequency or the real frequency? That's the real frequency. That's going to be FS. Good. We got another variable here. The speed of sound is 330 meters per second. That's going to be what? V, right? V what? V, well, it's not Vs, so it's got to be VW, right? It's the speed of the wave. Again, it's tricky here, right? Because we see that that's the speed of sound. We want to call it Vs. But Vs isn't the speed of sound, it's the speed of the source. Okay, we want to find the Doppler frequency here. Really, we want to find the change in frequency. But we'll find the Doppler frequency as it's approaching, as it's coming towards, and away. And then we'll subtract them. As it's coming towards, we're going to say FD is equal to, what was the equation? VW over VW minus Vs. Times FD. So we've got VW is 330 divided by 330 minus 30 times the Doppler. Hold on, what are we doing here? This should be VFS, right, over here, not FD. The actual frequency, the frequency of the source is 224. What do we get there? Okay, let's figure this out on the calculator. Let's get the bottom number first. We can probably do that in our head, but we'll do it on our calculator. Noise. 330 minus 30 is 300. We're going to say 330 divided by that number. Gives me 1.1. We multiply it by 224, and lo and behold, we get a number 246.4. That seems reasonable, right? The number is higher than the actual frequency, and it should be, because it's approaching, it's coming towards it. Now let's find the frequency, or the apparent frequency, the Doppler frequency, as it's going away from the observer. We're going to say FD this time is equal to VW over VW plus Vs. Plus, because we need a number on the bottom that's smaller in order to get a number, hold on, what's wrong here? No, sorry, we need a number on the bottom that's bigger. We need a number on the bottom that's bigger in order to get an FD that's smaller. So what do we got here? VW is 330 over 330 plus 30 times 224. What do we get there this time? We should get a number that's smaller, right, because it's going away from us. So we're going to say 330 over 360 multiplied by 224 gives us a value of 205.333. And now we've got to subtract those two in order to get the change in frequency. Listen, if you can do this question, it's about as hard as it gets. The one thing that could throw a little twist in this is rearranging it, but I'm not going to ask you to rearrange it to solve for VW or VS. That's a little bit further than I think that you're going to be able to do. I could ask you to solve for FS. That shouldn't be too hard, right? Because you just divide FD by everything that's in brackets. This is about as hard as it gets. We're going to say 246.4 minus 205.333 gives me 41.1. So as you watched those videos with the van going by and then the fire truck going by, you heard the frequency decrease, or at least the apparent frequency decrease, the Doppler frequency. If the speeds were these speeds and the frequencies were these frequencies, then you would find that it would have decreased by 41 hertz, a noticeable amount. Have a look at these two questions on page 432, and those will be the last two new questions that you ever have to do in Physics 20.